Okay, so hey everyone, welcome to Multimodal Weekly. Thanks for those who are attending live today, as well as those who will be watching, recording this session, afterwards. So this is a virtual webinar series initiatives hosted by the team at Troll Labs. For context, we are a Series A startup using multimodal foundation models for video understanding. We've been meeting on a weekly basis over the past 2 years or so. Here are the topics that we tend to cover on a weekly basis. New research in the field of multimodal AI and foundation models. Oftentimes we have developers and builders from our Discord community coming and talk about their respective projects that they build. We also have partners talk about different applications that they build, different verticals, and tutorials and guides on using the technology platform and API. For example, here's some of the recent session that we had. As you can see, we're arranging, especially on the research side, we're arranging topics that cover from long range video understanding to benchmarking, video language model to online learning to multi-shot video understanding. So a variety of different interesting topics. So for today, super excited to have the two speakers that will be presenting their work. So the first speaker is going to be Tianwei Xiong, who will present his work called LVD2M. This is the first long-text video dataset comprising of 2 million long-text videos, each covering more than 10 seconds and annotated with temporally dense caption. So you're probably aware that having good dataset is a very important criteria for high performance models. So yeah, excited to hear Tianwei and talk about the methodology and the impact of his benchmarking dataset creation process. And then as a second half of the webinar, we had Sukwon Yun, currently a PhD student at UC Chapel Hill. And fun fact, we have, I think just a couple of weeks ago, we have a couple of your colleagues from Chapel Hill here coming to talk about their work. So yeah, we have pretty good relationship with the folks over there. But Sukwon will talk about his work called Flex-MoE, which is short for Flexible Mixture of Experts. This is a new framework designed to flexibly incorporate arbitrary modalities combinations while maintaining robustness to missing data. So, as you know, we focus a lot on multimodal at 12 Labs. So, yeah, excited to hear more about some of the details, how the field is going in terms of combining modalities and new algorithms, new techniques to streamline the learning process, right? Between different modalities. So with that, yeah, for the attendees, feel free to send your question on the Zoom chat, and then we'll have a short, like five minutes Q&A after the speaker finish. So with that, I will stop sharing my screen, and yeah, Tianwei, feel free to go ahead and share the screen. Let me unmute you as well, by the way.
Okay, thank you, James. I have shared my screen.
Yep.
Okay. So hello, I'm Tianwei Xiong, and I'm excited to introduce you to LVD2 Million, a long-text video dataset with temporally dense captions. So LVD2 Million is designed to enhance the training of long video generation models. So it boasts 4 crucial features. First, length. All training video clips are at least 10 seconds long. And second, consistency. The clips are long-take footages without cuts, ensuring coherent video generation. And third, dynamism. Large motion and diverse content are incorporated to benefit video generation models. And fourth, dense captioning. LVD2 Million provides temporally dense captions to effectively condition the training of long video generation models. Okay, so here are some exemplary videos from LVD2 Million. So these long-take footages showcase highly dynamic and significant content variation. And for such intensive video clips, LVD2 Million provides temporally dense captions. Okay, here is one example. The caption captures the storyline of this long-take shot from the beginning to the end. Okay, let's watch it. So as highlighted here, so to start with the person holding the instructor's hand for support and then leaning forward as they begin to fall and eventually they fall onto the slow cover ground. So this is the kind of caption we may want for training a long video generation model. And similarly, this video and its caption capture a complete play in a one-on-one basketball game and showing these 4 action sequences as highlighted here. And how are the previous datasets doing? And if we compare with previous video caption pipeline like Panda 70 million and OpenSora, our captions are detailed and cover the temporal changes. So in this example shown here, a man enters a room and contacts with people in the room. Okay, so previous captioning pipelines, they fail to capture the full temporal content, which lacks the latter part, the man communicating with people in the room. And in contrast, our method performs well. And by more statistics, we can see how LV2 minute better meets the needs we want for a long-take video dataset. So compared to previous datasets, LV2 minute video data is significantly more dynamic, having less cuts and transitions inside the clip, and all annotated with detailed captions. Okay, so these are the numbers, and next I'm going to introduce to you our data pipeline. Our video data is collected from the open source datasets. So they provide video URLs crawled from the internet, timestamps for certain clips, and the corresponding one-sentence annotations. And we first pick all the clips that are longer than 10 seconds, and then we want to filter any clip with any sort of scene transitions by human edits. So like sync cuts and fade in, fade out transitions. These effects, we don't want them to be included in our data. So while filtering videos with cuts is a common target, but the previous methods didn't work very well. So here is a simple demonstration of the typical usage of PYSync detect algorithm used for detecting sync cuts. So it checks difference between consecutive labeling frames, and if the difference is big, a sync cut is detected. Okay, so here we can say this method fails for the fade in, fade out transition. And our solution for this problem is very intuitive. We check frames that are temporally far away from each other. So here specifically 2 seconds away, not frame by frame. And we use a higher threshold to recognize the same transitions. So how about the results of our method? We manually check the ratio of long take videos among videos longer than 10 seconds. And as shown in this table, a large portion of long video clips in existing datasets still contain scene transitions. And our dataset is much better. And note that the 3 baselines here listed here, they have already tried to exclude scene cuts in their video clips. Okay, so but the numbers are still not very good. And our method achieves better results, but it's still not like 100 or 90%. And a better long take video segmentation algorithm actually is still in need. So now we have long take videos. That's the first target. Then we want to filter static videos because they can be trivial and redundant, which is meaningless and even harmful for video generation models. Okay. So to find out how dynamic a video is, we first use average optical flow score, which is basically the average of the predicted moving speed of each pixel in the video. And in the listed examples, the videos with the low score are indeed not very dynamic. However, there are also examples with a relatively high score, but perceptually not very dynamic. As shown here, second row, first column. Yeah, the camera is moving, but perceptually it's not very dynamic. So how to solve this problem? To actually better align with human perception, we use video language models to evaluate the quality of a video clip including how dynamic it is and other metrics. So what is done here is actually very intuitive. We ask questions to video LLMs to check the quality of a video, getting yes or no, bad, good or bad answers. Like here, we check the content variation, want larger content variation, so we just ask a video LLM if the video is good enough. And here in this example, we check for better visual diversity and less text overlay. So basically our questions cover three aspects. And finally, we have this whole pipeline for video collection. Ideally, if the video is capable enough and the computation cost is acceptable, then all the video data filtering tasks can be completed with video LLM. Well, however, video LLMs, they are still computationally expensive and having trouble with instruction following and hallucinations, so it is still only a part of our data pipeline. Okay, now we have content-rich long-take video data. And to caption these videos, we first divide a long video into multiple segments and extract 6 frames for each segment as an image grid. Then we caption each segment individually using Lava receiving image grid as input. Then we use an LLM to compose the multiple captions for the multiple segments into a single compact and temporally dense caption. And in this example, the actions observed in each image grid are integrated in the final caption. And this video is about like 2 minutes long, and I'm not going to play the full. And this is for them. It's just a demonstration. Yeah, this is how we caption our long videos. And here is a more detailed comparison with previous datasets. Our videos are overall more dynamic than previous dataset according to user study. Okay, the dynamic score much higher than previous datasets, and our captions for videos are also more preferred against the previous dataset captions. Okay, the most of them, the baselines, they are basically like one sentence captions. And the aesthetic score of our videos are also better than HDVG, which have used calculated aesthetic score for filtering. And about aesthetic score, we only used VQA to ask it about the visual diversity. And we try to fine-tune a text-to-video diffusion model on our V2 million, which gave us a promising result. So here we fine-tuned a base model pre-trained on 32 frames. For fine-tuning, we use 65 frame video clips to extend the generation length. So under the same setting, fine-tuning on LVD2 million produced a better generation model compared to WebV 10 million. Okay, so WebV 10 million may be currently the public best choice for training video generations on longer frames. And compared to WebV 10 million, we can say that like in the this second row have better shapes, better motions, and better consistency. Okay. And quantitatively, our results are also better on VBench. So the model trained on LVD2 million excels in dynamic degree, object class, and human action as highlighted here. Okay. And here, lastly, I want to talk about the future research. Okay. So the ultimate goal for the long take video dataset is word model, a model that can understand and generate a physical or any sort of self-contained world. And many challenges remain to be solved here. One thing is the long take video understanding. So for our dataset, we use a composite captioning pipeline to annotate long videos. But ideally, this will be done by a single model. Okay, so currently we still don't have intelligent agent that can look at a video frame by frame, and then it can summarize the content of the video and by checking it frame by frame. It's still this is still not achieved, or like not having very satisfactory results. Okay, then that means we will have difficulty having a model understanding the whole video well. And second, the effective compression and generation of long videos. So actually, although we have video clips longer than 10 seconds and even 2 minutes long, it is still very costly to train video generation models on video clips longer than 10 seconds. So there are too many frames and too many latents there. The memory cost will be huge. So there needs to be a more efficient way for long video modeling. Like we we may need better video compression algorithms to smartly compress the video, considering its temporal redundancy, a smarter way for compression, so that we'll have less latency to model for long videos, and so the burden for generation models won't be that large. Okay, so I think there are still many challenging tasks for the use of long take videos. And yeah, thank you for listening, and welcome to utilize LD2 Medium for research. And I have gone through the content a little bit quickly, so I guess I'll spend more time on the QA part. Okay,
All
thank
right.
you.
Yep. Thanks a lot, Tianwei. Really appreciate you walking over the talk. Yeah, for the participants, if you have any question, feel free to either unmute or just put on the chat. Maybe I get started with some seed question. So, can you go back to the slide on the pipeline again, the data curation pipeline?
Okay.
Yeah. So it looks like you curate like a bunch of these like long text videos from these four sources, right? WebVid, Panda, InternVid, and then you do some sort of like pre-processing with these curate clips, and that become LVD2M, right?
Yes.
And identify long text as more than 10 seconds.
Yes, so these data sets they crawl videos from the internet, and naively segment them into clips, and we also very naively just to pick the videos more than 10 seconds and just filtering out any clip containing any sync cuts or transitions.
Yeah.
So of course, there will be a more efficient way of using this data. So of course, we have wasted many data because many long video clips, they may just contain one sync cut. So we just separate it into half, but we just choose to filter out any clip with a cut. So just as I said, a smarter algorithm, segmentation algorithm is still needed.
Oh, I see. So for the filtering part here, did you like have an algorithms to filter that out, or do you like manually like figure out which video
Yeah.
have the scene cut? Yeah, like yeah. Oh yeah, I think go ahead.
So this is what we do here. So we what we actually do in practice, we collect a small set of videos. We label the existence of sync cuts. So we have a small set of videos and labels, and we adjust the detect interval and many hyperparameters, the threshold,
Yeah.
to fit in this small data set and then generalize it to a larger data set.
And the threshold here is that like a static number? How do you determine that threshold?
So we need to calculate the difference between frames, right? If the difference is big, then we figure there might be a sync cut between the two frames.
Mm-hmm.
And about the calculation of the difference, we use PYS index algorithm. We calculate difference in the RGB or HS with space plus the the detected age, the difference. So there will be a number here. We set this number to be higher because we use a larger interval. So there will be a higher threshold to detect the difference. Okay, so this is
Mm.
how we do this, set the parameters.
Very interesting.
Mm.
I see. So by that, I was taking a look at that by scene detect GitHub repo. Looks like it's like an open source repo where you can like
Yes.
just code, right? Detecting scene changes, etc.
Mm. Actually, for this problem, there are two kinds of solutions. One is POS index, so you can see many manually crafted rules for this kind of problem. And there will also be neural network-based methods. But neural network-based methods, they do well for detecting jump cuts. So,
Mm-hmm.
because they predict the position of the jump cuts. But for this scenario, the fade in, fade out transition or many other very complicated human edits here, the transition effects, I don't know whether they perform well because they are not trained on such data.
Right. Can you go to the next the slide on captioning, the captioning of the
Okay.
clips? Yeah, this one. Yeah.
Yeah.
So you use scene detection, right, to break the long video into images, and then for each of these image grade, leveraging Lava for basically like image level captioning, right? And then the output of that image level captioning will be fed as input to plot to come up with like a synthesized overall caption for
Mm.
the whole like uh, sequence of frames, right? That made up of this image grid, right?
Yeah. So, well, actually, people may be curious why we are using an image LLM to caption videos. We have tried video arms, like we have tried video arms using in our data curation pipeline, but we didn't use it for captioning because video arms they suffer from severe hallucinations when they are asked to do captioning. So maybe they perform well on VQA tasks. They can answer certain question about the video, but
Mhm.
if you start to ask it to tell you every detail inside this video, what is exactly happening in this video, then it may produce very severe hallucinations. So that's
I
why
see.
yes, that's why you are using Lava because it is trained on larger scale data. It has better instruction following. That's
Mhm.
what use Lava.
And how did you like fit them into Cloud? Did you like use like a prompt to say, hey, given all these caption, like combine them all together, or like what's that process look like?
Hmm. So yeah, we in our prompt we just tell it, we have input an image grid and um we tried not to tell it how the image grid is not shaped here, and just tell you an image grid with several frames and just let it to check these frames and just tell us what is exactly happening, and we will add many prompts that to pay attention to the camera perspective and the background and how to how do you organize these tags into a caption for video, that kind of form.
Yeah.
So yeah, we have designed a little bit complicated prompts, but I believe that may be specific for Lava. But if like you are using more advanced models like GPT-4o,
Hmm.
I think there will be less prompt engineering.
Got it. Okay, last question from myself. So in the last slide, uh, the second to last slide that you have,
Uh, Second
yeah,
last.
this one right here. So these are basically like future direction, right? What are the limitation of um yeah, like what's next for long text video? I think I guess you mentioned briefly in the presentation, but like we need better video LLM for long form understanding, right?
Yes.
And what does it mean by effective long video compression here?
Yeah. So effective, by effective I mean efficient. So like if you are compressing a long video into latents for diffusion models or codes for large language models, for these models to modeling the generation, well, you'll find that you are producing a very, very long sequence if you are producing long video. And actually, that is very problematic for diffusion models or LLMs to learn because it's very obvious that they are very redundant. Because a video, how we model a video is very temporal redundant. After we have seen the first frame, we have got most of the information, and for the frames following it, the additional information is much less. So there should be a smarter way to model this long sequence. And actually, in practice, the sequence it is just too long, and it's just not affordable for even some big companies.
Yeah. And the reference here on like Cosmos, that is the one from NVIDIA, right? If I'm correct.
Yes. Yes.
So do you think War model will be an efficient architecture to, you know, do long form video compression?
Well, I guess the war model is a final target, but
Mm-hmm.
when we are talking about the efficient algorithm, Cosmos didn't really, study into that. So and just the temporal redundancy, just like I have talked about, that has not been solved. And in Cosmos, they still don't generate videos longer than 10 seconds, right? So that is still a problem, I guess.
Mm-hmm.
The efficient algorithm problem need to be solved during, heading towards world models.
Let's see. Yeah. Right. I think that's all the time that we have for Tianwei. Awesome. Thank you so much. I really appreciate your
Thank you.
presentation. Super exciting work. And with that, I will pass it to the second speakers. So Tianwei, yeah, go ahead.
Okay, so I will share my screen.
Yes, go ahead.
Okay, so could you see the slide of the
Yes.
Flex-MoE?
Yes, we see it.
Okay. Oh, yeah, so it's my great pleasure to share and discuss our work, Flex-MoE, into the 12 labs. And currently I'm a first-year PhD student working with Professor Tianlong Chen, and my name is Sukwon Yun. So today I will go through the Flex-MoE, which is modeling arbitrary modality combination via the flexible mixture of expert framework. So this is accepted last year in UX as a spotlight paper. And this is the collaboration work with the University of Pennsylvania and USTC. Yeah, so before we dive into the Flex-MoE, I wanted to give a quick summary, one slide summary of our Flex-MoE work. So the motivation is like, given a multimodal nature, existing works solely focus on the single modality or just rely on the fully complete modality samples. So in this scenario, so we thought of how can we model arbitrary modality combination in a more natural and more tailored way. So idea is like we proposed the Flex-MoE. So this is the MoE framework where the modality combination now becomes a separate expert. So the Flex-MoE consists of missing modality bank completion, expert generalization, expert specialization. So I will give more details on each procedure in a later slide. So this is the main illustration that could summarize our work would be this like a we would have like 4 kinds of modality like C, clinical, biospecimen, image, and the genetic. but existing work solely focus on like just utilizing only the one modality, or just mainly relying on these fully complete samples. So this is only the partial sample of the whole data set. So we want to focus more on the other regions where the modality combination is made with different modalities. And given this scenario, our idea was like compared to vanilla mixture of expert, where we have a router and expert. And expert is just the one of, you could think of the MLP layer, which is specialized on each scenario. But we, compared to vanilla MoE, Flex-MoE designed each expert as a modality combination. So we want to have a much more tailored way, so more specialized, expert being more specialized in each modality combination. So to begin with, we are now living in a multimodal era. So for example, we could see, we could hear, and we could touch. So given this like a multimodal situation, it is very much natural to obtain many kinds of data sources. So it could be like a text, audio, graphics, and video. So like the video here is the current focus of the 12 labs. So video itself for sure have like various modality in itself. So this is the multimodal era we're currently focusing on. And currently in this Flex-MoE work, we focused on like, for example, in the medical domain, when we classify the Alzheimer's disease stage of the patient, it could involve clinical, biospecimen, image, and the genetic modalities. So how we combine these modalities well is the main challenge of the multimodal scenarios. So given this multimodal nature, we especially targeted the missing modality scenario. So we case study this Alzheimer's disease neuroimaging initiative called ADNI dataset. So this is like the statistic of each patient belonging to each modality. So we could see 2,000 patients are having the clinical modalities, while only like 1,500 samples are having a genetic modalities. So while we have a like an intersection, calculate the intersection samples, number of samples given these four modalities, there only exists like 1,474 samples. So not just leveraging this intersection data, we wanted to model these other regions as well. How could we leverage these other regions better with the MoE framework was our key motivation. So the problem here is like existing works facing is they fail training with incorporating other regions, and also thus correspondingly like it would fail the inference of given diverse modality combination when the inference phase comes in. So the motivation here is like, for example, as a case of the medical domain, this region would be the patient with the clinical plus biospecimen, and this region would have their own circumstances. Like if the patient belonging to this area, they would be like, for example, related to early diagnosis of AD. So we want to make some specialized knowledge, inject some specialized knowledge in each region. So that was the goal of this project. But before we dive into Flex-MoE, there is some existing works in a multimodal domain with targeting the missing modality. So currently, this work published in a CVPR 2022 showed the multimodal transformer fails when the image and the text modality becomes missing scenarios. So we could see the performance drop when the missing scenarios occurs. But the problem here is like they do not explicitly model the modality combination as itself in the fusion layer. So while transformer encoder is this transformer encoder is proceeding all the modality combination all together, so it would not have specific knowledge of like image only and text only, image plus text, like this kind of modality combination. So we wanted to design much more better fusion layer of the transformer by using the MoE. And for sure, like there exists some other works that could alleviate these missing scenarios, such as using learnable embeddings to impute the missing embeddings, and also knowledge distillation of using the teacher and student network given this observed and the missing modalities. And for sure, there could be like a following the lead, where the different modalities would have different significance. We could follow the lead of the specific modality information. And like another branch of the existing work could be like using graph aggregation. So solely using the observed modality information given this sample, we could design some bipartite graph, and also given this embedding of the observed modality, we could also do some kind of feature alignment. But the thing here again is like they do not focus on the modality combination, where each modality combination would have specific scenarios, circumstances they have to be specialized in. Then also they could be explicitly generating the missing modality branch. So it could consist, like having the shared encoder, they could generate the missing embedding. And also using the diffusion framework, they could also generate the missing embedding. So this is a currently ongoing works of the existing works on the missing modality in multimodal domain. But ideal scope we wanted to focus on is like, rather than just focusing on this complete data, we want to model these arbitrary modality combination in each region much more better way. So we come up with think of the mixture of expert framework. So this is the quick summary of the background of MoE. So when the input comes in, there is a gating network called router. So the router only activates the relevant expert. For example, if the top K was the top 2, we just activate the most relevant top 2 expert to obtain the output. So we could think of this expert is very much specialized and tailored to the given input. So this top K activation is like when the top K is in the selected expert, we just use this value, while otherwise we just use 0 values to sparsely activate only the relevant experts. So this is where the efficiency comes in. So we only activate the relevant expert in a sparse manner. So this is our overview of the Flex-MoE. So this currently consists of mainly 3 steps. So missing modality bank completion and expert generalization, followed by expert specialization. So to begin with, we first sort the samples with the full to few order. So this is motivated by this curriculum learning framework, because we thought samples with the full modalities would be much more beneficial to train the model, and would have much more insightful information that could be delivered to other patients as well. So given this patient and the modality information, we first pass through this modality-specific encoder and then obtain the embedding. So this would be like this black sample have the full modality input from the raw feature space. So we obtain the embeddings from each specific encoder. So we would have embeddings. But the problem here is like this gray and the white patient sample would miss some kind of embeddings since they do not have the observed modality in their initial state. So since the later stage, we would have to play with the sparse mixture of expert framework. We could think of just having a 0 padding, but in this project, we use some learnable embeddings framework that is designed like this lookup table as like this. So the row belongs to the observed modality combination in the specific situation, and the column is their corresponding missing modality. So for example, in the second row, this patient is having image, biospecimen, and genetic. So IBG as an observed modality combination, and C as a missing modality. So this is the region where the runnable embeddings would be responsible for imputing this second sample. So we do this in we call this missing modality bank. So the rationale behind using this bank rather than just padding would be these runnable embeddings would have more contextualized and specialized information given this modality combination nature. So if the modality is observed, we just pass through the encoder. And then if the modality is not observed, we use this missing modality bank, which is consisting the learnable embeddings. And then we have just soft learnable embeddings imputed within each patient. And then we move on to expert generalization. So this is where the rationale behind we sort the samples within the full to few order. So we first leverage the samples with the full modalities. So given this patient, we just pass through just vanilla MoE, where the experts is now the specific modality combination. So this is just you could regard this G router as the vanilla MoE. So we just let the router automatically selects the most relevant expert within a top K manner. So this is we just warm up the expert training with leveraging the full modality samples. So each expert would have opportunity to warm up their initial parameters with the full modality samples. So we leverage this information more to training the expert in a beginning phase. And then this is where the key highlight of this Flex-MoE comes in. So given this warmed up trained expert, we now specialize each expert, because the main goal of this expert as a separate modality combination would be to have specialized and contextualized information to be captured in each expert. So when the samples with the IBG comes in, for the top one selection, we let router to be selected as a top one select as an IBG expert. And then for the remaining top K selection, we just let the router to select other modality combinations, so that they could harmonize and then have a synergetic effect of the final output. So in the case of the sample with the C modality, for the top one selection, it would automatically select the C as the top one selection, and then remaining top K-1, the router would automatically decide which expert to activate. But here, little technical contribution in this expert specialization was if we manually interfere this top K selection procedure, the gradient flow could be canceled out. So we wanted this Flex-MoE is an end-to-end framework. So we want this gradient flow to be continuous. So we just use this cross entropy loss. So if the IBG comes in, we track the top one selection, and this top one selection should be mapped with their specific index. So by using like a cross entropy loss. So this cross entropy loss is sum up with the task loss and being trained all the way in the end-to-end framework. So for the result parts, we did some experiments on the ADNI dataset and also the mimic dataset. So given this like a modality combination with the various combinations like IG, IC, and IGC, IGCB, we could observe Flex-MoE could achieve very much outperform existing baseline within various scenarios. And for the ablation study, we also did some ablation on the not including expert specialization and not including expert specialization plus expert generalization. So we could see if we do not specialize this expert, the performance very much goes down. So this tells us expert specialization is very much key, a module that could improve the performance. And this is the sensitivity analysis of how much expert we should use for the MoE framework and how much layers we used, how much top K selection we should leverage. And this is the plot we showed in the paper. So given this, to recap the missing modality bank, the row and the column in a matrix manner. So we just, after training this MoE framework, we look into the missing modality bank embedding and then calculated the cosine similarity within each row and each column. So we could see we could have some insight where the samples having ICBG and samples with the C having a very similar context compared to other combination. And also if the patient's missing G and C, that means they are having much more similar context compared to other scenarios. And this is the plot we could see the expert having not only the generalized knowledge by having a full modality warm-up stage. So this mint color is the knowledge of the BCGI, where we want this BCGI information to be injected from the expert generalization module. So we could see through these experts, they have their knowledge of this BCGI. And also for example, if the BCG expert in this case, this BCG expert not only contains the full modalities, but it is also specialized in each specific modality combination. So that means BCG expert is responsible and very well trained when the input is the BCG modality combination comes in. So this is the plot we showed in the paper. And by using this sparse mixture of expert framework, we could benefit from the less number of the G flops, since only the sparsely activated expert is responsible for the output calculation. And also compared to other baselines, we have a less number of parameters to be used in the training. So we could see Flex-MoE not only have an effective performance, but also achieve the efficiency perspective. So this is the summary and the limitation of the Flex-MoE. And for the summary, existing works either focused on the single modality or fully complete modality samples. So given this motivation, we designed the Flex-MoE, where we treat the modality combination as a separate expert in a MoE framework. And it consists of missing modality bank completion, expert generalization, followed by expert specialization. So we evaluated Flex-MoE in the ethnic and the mimic data set, and then we could see in a various modality combination, Flex-MoE outperforms. And trained expert not only contain the generalized knowledge, but also contain the modality combination specific knowledge, which was our main motivation of this work. But at the same time, we could also think of some limitations that Flex-MoE work has. So the first one is like when the number of modalities increases, that is naturally the number of modality combination would increase as well. So that in this Flex-MoE work, the modality combination itself has been treated as a separate expert. So the number of experts would be super large when the modality is like over like a 10 or 20, which could be in a near future. So this could be one of the limitation of the scalability perspective. And second one is the limited training samples available for each modality combination, because this IBG training, we need, in an ideal case, to train the IBG expert well, we need a bunch of IBG samples to train this IBG. But if the training samples is limited, we could not expect the generalizability of this IBG expert. So the potential remedies for the limitation could be if the number of modalities grown up, we could think of some merging this modality combination. Some sparse, like if these two regions are sparse, we could just merge these two modality combination and then regard them as a one merged expert group. And this could be the remedy for the first direction. And for the limited training samples, we could think of some augmenting the samples. And also at the same time, we could merge some modality combination training samples and then use it as a much more smaller and a higher number of samples within a group. So yeah, so thanks for listening. And if you have any question, I will be happy to answer more. Thank you.
Awesome. Yeah. Thanks a lot, Sukwon, for super details coverage of the work here. So I will, yeah. We have about 5 minutes left on the webinar. So for participants, if you want to ask questions, feel free to unmute and ask Sukwon. So maybe I can get started. I think one of the slides you mentioned, well, first of all, the framework that you present here consists of multiple steps, right? So you have to treat each modality as its own unique pipeline, and you do a lot of different things, from like completing the modalities to like generalize and specialize pipeline for that specific modalities. So I'm curious, like out of different phase of this pipeline, which phase is the most like technically which phase is most technically complicated to implement?
Oh, okay. In the implementation side.
Yeah.
Yeah. So I think during designing this framework, like for sure, like we could first start with the vanilla MOE structure, but the thing is like when it comes to the vanilla MOE, the router and expert being selected is like automated by this router. So we want like a key contribution in this work should be like expert as a modality combination to be specialized. So we need to interfere this top case selection framework procedure. So we first like just manually like select the top one. We just tell the router the top one selection given this IBG should be IBG. But when we manually interfere like in this situation, the gradient would be canceled out because router automatically selects the expert selection procedure. So we come up with the alternative, such as using the cross entropy loss. So after we just let the router select the top two selection, for example, and then we track the top one selection, and we just softly tell the model like the top one selection should be the index where the IBG is currently located in. So we use the cross entropy loss to have a much more to do not cancel out the gradient flow. And interestingly, it turns out like through the ablation study, this expert specialization had a very big contribution on the overall improvement.
Yeah. And I know for each modalities, you have a specific encoders, right? So for example,
Yeah,
image encoder, clinical encoder, etc. What are those encoders? What's the architecture? What's the model to use for each?
yeah. So like we use for the image encoder, since like for example in the any dataset it's like a patient's MRI image, we use the 3D CNN as a backbone model to extract the embedding. And for the clinical biospecimen and the genetic data source, like you could think of each data source is like a matrix format. So we just leverage just a simple MLP layer to have an embedding for each modality.
I see.
Mhm.
Got it. Perfect. I think you mentioned that one of the limitation, if we go to the last slide, the limitation part, scalability. Yeah. So I think the issue here is like when you do the missing modality bank, you have to when you do the modality combination, yes, like right now there's only 4, right? So it's easy to combine them. But if you want to add additional modalities like so audio or video, right, then the modality combination will double or triple, right?
Exactly.
So how do you think about intelligently solving that problem?
So yeah, that's the like a straightforward limitation and also like a potential area we should look into. So the naive idea we thought is like if the sparse like there exists some sparse combination, modality combination. So for example, like in this case, like 21 and 122 samples are being located in this region. So naive idea is like we just merge these two regions into the single region, and then to reduce the total number of modality combination. So in that way, as the number of modality combination decreases, the corresponding number of experts to be trained on Flex-MoE would also decrease. So this merging technique could be a one way of this alleviating this issue. And for the technical side, there is a lot of ongoing works in a MoE area, like how we merge the expert within a more compressed way. So we could think of utilizing that kind of MoE specific technical details in a merging technique into this current framework.
Perfect. Yeah, that makes sense. Okay. I guess the last question I have before we close out the webinar, I was just taking a look at your website, your personal academic website. It seems like you focus a bit on like multi-agents, LLMs, right? And yeah, I saw like some of your recent papers. It's like symbolic MoE, generative AIs, and MoE, right? So it sounds like mixture of expert is like your favorite topic of research direction. Yeah.
So I think it would be great opportunity for in a future seminar if I could introduce the symbolic MoE work as well. So that's kind of like using MoE structure in a multi-agent LLM framework. So like given the question which agent we should activate to solve the input query is like a key contribution in symbolic MoE, but that could be formalized in a MoE framework. So yeah, I think if time allows, I think in the later seminar, I would be happy to introduce this paper as well.
Yeah, super exciting. We'll hear. All right. I think that's all we have for today's session. So I will thanks again, Sukwon and Tianwei, for spending time with you today, with us today, and over the talk. The recording of this session should be available in a week or so. So be sure to share with you guys the link when it's available. And yeah, the virtual series is happening every Friday. So stay tuned. If you found this information informative, we can join future session and learn more about new research. All right. Thank you, everyone. I will stop the recording.
Thank you, James.